Okay, welcome everyone. So today we're going to be covering gases, liquids, and solids, and using some rather simple but uh, powerful laws to understand how physical forces, so thinking of things like pressure and volume, and temperature, and how they relate to these three states. So let's start off by just recapping the three states of matter as we discussed. On several occasions, we have gases, liquids, and solids. There is a fourth type of matter, but again, for chemistry, we simply don't um, care about that guy. Now, gases have a not definite shape or volume, and they expand to fill their container. Now, the arrangement of molecules in a gas is randomly arranged. Things are constantly moving in a gas, and they have typically low densities. And the particles themselves don't really interact with one another. And when I say interact, I simply mean colliding with one another. And then we have the liquid state, which is a state which we have a fixed volume that takes the shape of its container, and the molecules themselves are randomly arranged, and the density is typically high, but there's pretty strong interaction between the particles, so the molecules in our liquids, which results in relatively moderately fast speed of molecule movement. And then we have the solid shape, which has a definite shape and volume, where we have a fixed arrangement of particles that are very, very close together with a high density, very, very slow movement of these molecules, and very, very strong interactions between our molecules. So a little bit more nuanced of a definition than what we've seen previously, but again, building upon what we've seen. So just to sort of visualize what we see, we have silicon dioxide here. As you'll notice, it forms a pretty definite shape, almost a crystal-like structure. You notice it forms kind of like a snowflake shape almost. But lots of interactions between these molecules as a whole. We see liquid water here. The molecules are still close together, but have a random shape, and they are interacting with one another. And then we have see in the final state here a combination of nitrogen and oxygen gases, much farther spread apart, moving very fast, not really interacting with one another. Now, the balance between these three, as you might imagine, is simply the balance between kinetic energy of the particles as well as the strength of the interaction between these particles. So as we go from left to right here, so this way to this way, the molecules are moving faster and faster. Conversely, as we go right to left, the interaction strength between these particles increases. So that's the generalized patterns we see for our states of matter. So again, a much more nuanced definition than what we've been working at thus far. So let's start with gases. And we can actually talk about gases by using a very special theory, which we call the kinetic molecular model of gases. Now, building on what we've seen, this theory tells us that gases consist of particles. Now, particles in our cases are atoms or molecules, either or, and they are moving randomly and rapidly. And I mean randomly. Think about if you threw a tennis ball against a wall, it would bounce and then hit, it bounced again, it would bounce randomly all over the room. That's what we mean by moving randomly. And rapidly simply means just moving fast. Now, the reality here is that when we're thinking about molecules and when we're rapid movement they do. Now, these gas particles do exert no attractive forces with one another, and that simply means they're not essentially hitting one another, interacting in any meaningful way, typically. The kinetic energy of gases will increase with increasing temperature. Now, kinetic energy, as you recall, is just the energy of motion. So as we increase temperature, these molecules have more kinetic energy, thus they are moving faster. Now, the final thing about this theory, and it states that when molecules or gas particles collide with one another, they rebound and travel in a new direction. So, for instance, if you manage to say smack two tennis balls against one another in the air, they'll collide and bounce and repel one another in completely different directions, very much like a gas would. So that's our kinetic molecular theory. And we can describe this with actually a relative number, a small number of terms. And because this is chemistry, we describe this with math, of course. Now, remember, our gas particles, they have the capacity to collide, not very commonly with one another, But if you have a gas in a room, in a container, a cylinder, or wherever it's in, the gas molecules will hit the wall. And when something hits the wall, very much like if your finger hits a table or a finger hits the wall or anything, it exerts a pressure. And so you guys probably have an idea of what pressure is, but it simply refers to the amount of force that you apply per unit area. So the way you can sort of think about this in your brain is if you take your index finger and apply it to your palm and you press down with an amount of force, you're pressing down with, say, 5 pounds of force on your palm. Now, the reality is you could press down with the same amount of force with your palm on your other palm, and it's not as much pressure. Why? Because the area at which you're applying that force is greater over a small area than it is over a large area. Hence, the pressure is higher. So same force exerted over different areas. And so thus we can mathematically define pressure as force divided by area, or F divided by A, and pressure is simply denoted as P. Now we have a couple terms that we're going to a couple of units we'll make mention of. So the one that you guys probably most commonly hear is PSI, or pounds per square inch. So when you fill up your car tire or a bike tire, it's always in pounds per square inch. Now, the other common thing you'll hear is actually millimeters of mercury, or mmHg. This is what blood pressure is taken in, um, millimeters of mercury. And then there's other couple units, torrs and pascals. We don't commonly see those very much. Pascals is very much a physics unit, and torrs is a much more of an atmospheric science term. So we don't really use these very commonly. But the one we will actually use quite a bit is our friend, the atmosphere. Now, one atmosphere can be expressed as being equal to all of these different quantities. So as a general rule, we'll be working in atmospheres for this course. Now, to describe pressure, to describe gaseous movements, we're going to first talk about Boyle's law. Boyle's a very interesting scientist. If you've never heard of him, I recommend taking a stroll down Google to learn a little bit about Boyle. As with most scientists from a long time ago, he is a very interesting man. But what Boyle's law tells us, and we can mathematically express it as such, P times V equals K. And so what this tells us is for a fixed amount of gas that is applied at a constant temperature, the pressure and volume of the gas are inversely related. So thus, as pressure increases, volume should decrease. As volume increase, pressure should decrease. That's what that means. Now you'll notice that it's pressure times volume equals K. Now K is a constant. It doesn't really matter why it's constant. Just know that it's equal. K is a constant, and it has a mathematical value. So that's Boyle's law. K has, just as I mentioned, has a fixed value. Doesn't really matter so much what it means or why it is what it is, but just know pressure times volume equals K. Now, we can apply this in a fashion where if the volume of a cylinder is halved, the pressure of that cylinder should double. Now, we relate that actually back to Boyle's law here. P times V equals K. And again, if the pressure is halved, the volume should increase by twofold, and vice versa. Why? Because it's always equal to a constant K, and K never changes. Here, and a pressure of 1 atmosphere here, and a pressure of 2 atmosphere here. And so what changes between these is the decrease in volume. Now remember, as Boyle's law tells us, um, as volume decreases, pressure should go up. And that's exactly what we see. Volume decreases from 2 liters to 1 liters, and pressure goes up from 1 atmosphere to 2 atmosphere. So another handy dandy equation that we can derive from Boyle's law. If we have a closed system, which in this case we have a system where there's no extra inputs and it's at a constant temperature, we can apply Boyle's law. So let's do a little mathematical example to apply Boyle's law to calculate a new volume of pressure. So the question tells us if a 4-liter container of helium gas which is that gas that fills up balloons and gives you a funny voice if you inhale it. It has a pressure of 10 atmospheres. What pressure does the gas exert if the volume is increased to 6 liters? So we need to identify what we need. And the question asks us what pressure we have. So we have our known quantities and we have our desired quantities. We know volume 1 is 4 liters. We know pressure 1 is 10 liters. That's what it tells us from the first part of the problem. And then we know volume 2 should be 6 liters. So all we need to solve for here is pressure 2. So we can set up our equation. P1 is equal to V1. P1 times V1 is equal to P2 times V2. And we can rearrange this equation by dividing both sides by V2 to get P2 all by itself. And then we simply solve the equation, plugging in 10 atmospheres, 4 liters, and 6 liters. The liters cancel out, thus giving us a grand total of uh, I don't know. I forgot to do the problem now. So whatever 40 divided by 6 is, giving us that answer in atmospheres. So that's how we apply Boyle's law. It's a very, very simple law. The pressure you start with and the pressure you end with should be proportional to the volume and you start with and the volume you end with. And remember, Boyle's law is all about a consistent temperature. If temperature changes, as we will learn, we have to apply a new law. And we'll get to that in just a moment. Now, I actually want to talk about how Boyle's law applies to you, because it actually applies to something you do every second of every day, which is actually breathing. Now, to inhale, you don't really think about this on an everyday basis, but what happens is when you suck in oxygen or just air, your rib cage expands and your diaphragm, which is simply a muscle, drops. What this does is causing a net increase in the volume of your lungs. Now, because your lung volume increases, this causes the pressure in your lungs to decrease. Remember, as volume increases, pressure has to go down. Now, because there's a pressure deficit in your lungs, this causes air to come through your nose, through your mouth, and down into your lungs, thus drawing air into your lungs. Now, when you exhale, your rib cage contracts, your diaphragm is raised back up, which decreases the volume of your lungs. As you decrease the volume of your lungs, pressure has to increase. Remember, they're related inversely. So pressure increases, causing you to expel the air out of your lungs. So this is how you breathe, right? There's muscles involved, but what actually is happening is just changes in pressure and volume, which again, we can describe with Boyle's law. So a fun way to apply this very first gas law to your average everyday life. Now, our next law that we're going to talk about is our friend Charles. He's less interesting than Boyle, but you certainly can Google him if you have any interest in him. And Charles' law tells us for a fixed amount of gas, again, there has to be some constant here. In this case, it's going to be a constant pressure. The volume of the gas is proportional to its temperature in Kelvin. So we can express this as volume divided by temperature equals our constant K. So the pressure has to remain constant, right? That's not factored in here. If pressure changes, we have to use a different equation. But the equation will sort of wrap all these together. Will be coming in a few slides. So think about this. If volume is 5 and temperature is 5, they equal 1, right? That would be our constant. But if the constant never changes, as I increase volume, I have to increase pressure with it, right? So if volume goes up to 10, temperature also has to go up to 10 as well. So they have to change proportional to one another. And so we can actually look at this and express it the exact same way is as we did with Boyle's law, is we can look at the initial conditions in a defined scenario, and it should be equal to the conditions in a new scenario, right? So we have V1 over T1 equals V2 over T2. So in this hypothetical example, as we have a temperature at 200 Kelvin and a volume of 1 liter, if we increase the temperature here, right, because of this law, the volume should also increase with it. Now you'll notice that that something's likely going on with the pressure as well, but It's actually, remember, the pressure here is consistent, right? What's changing is not the pressure, it's just the volume, right? Our pressure is kept is held constant, but again, what changes is our volume and temperature. So as temperature goes up from 200 to 400, the volume has to double as well, and that is what our friend Charles' law tells us. V1 over T1 is equal to V2 over T2. Now we can actually use this to understand a little bit about why land and the sort of the interface between land and the ocean actually leads to sort of some interesting weather patterns in the ocean and along coastal lines. So as air comes off the ocean, it's typically cooler, but as it moves over the ocean, as it moves from the ocean to the land warms it up a little bit, which causes it to expand. And from an atmospheric standpoint, when air warms, air rises. I'm sure you guys have probably heard that before. Now, next up, we have Gay-Lussac's law. Now, Gay-Lussac's law tells us that for a fixed a fixed amount of gas that is at a constant pressure, the pressure of the gas is proportional to its temperature in Kelvin. Now, what you're probably noticing that we have another constant, which is K again, and we have for these first three equations, they've all been equal to K, right? And so they all must be related in some way, shape, or form. And on the next couple slides, we'll get into how we rope all these laws together into one nice simple equation. But what this tells us is P divided by T is equal to a constant, or pressure divided by temperature is equal to a constant. So very much like Charles' law, as we increase pressure, temperature should increase with it. Why? Because it's equal to a constant, and the constant never changes. So the reality here is we can also express it as P1 over T1 is equal to P2 over T2 in such a way that as we increase the temperature on a set pressure, from a pressure of 1 atmosphere and a volume of 2 liters, but we hold volume constant, as we increase the temperature, the pressure here should increase. Now, conceptually, why does the pressure increase? Well, remember, pressure in terms of a gas refers to those gas molecules bouncing off the container. Gas molecules bouncing off the container is pressure applied to a container. So as we increase temperature, that increases the kinetic energy of our gas molecules, which means they're moving faster, which means they're more likely to hit the container, thus exert more pressure on a container. P1 over T1 equals P2 over T2. Now, we can combine all three gas laws into one nice, beautiful equation where we simply define P1 over V1, P1 times V1 over T1 is equal to P2 times V2 over T2, where the initial conditions are proportional to what happens in the new condition. Which tells how fast they're moving. So all really, really nice, sort of wrapped together. And so this is just a handy dandy table of those three gas laws that we talked about, plus the combined gas law. The reality is you really only need this final gas law, right? When you're, say, doing an exam or something like that, this is the only one that really matters, right? Now, there's an important thing here is for this combined gas law, the amount of gas molecules or moles of the gas, which we define as N, is constant, right? They all have some constants here. But one thing they all keep in constant is the number of moles. But we can actually add a brand new term to this equation, thinking about how volume relates to how much material that I have. And this is Avogadro's law, which states that when the pressure and temperature are held constant, the volume of a gas is proportional to the number of moles present. Now, what this tells us is if I have a mole, which remember Avogadro's number is 6.02 times 10 to the 23 molecules, as I increase the amount of molecules, well, I increase the amount of volume they occupy, right? So picture you have 5 jelly beans, and then you go to 10 jelly beans, and then to 5,000 jelly beans, right? The more jelly beans you add, the more volume they take up, the more space they take up. And that's the same with the number of molecules or the number of moles. As they increase, then the volume they take up increases as well. So we can define Avogadro's law as the volume divided by the number of moles. Now, the number of moles is denoted by N, and it's equal to a constant, simply K. So that's Avogadro's law. Now we can conceptually look at what this looks like, and we can express it the exact same way we've been expressing it before. V1 over N1 is equal to V2 over N2. So if we have 1 liter with 1 mole of a gas, if we increase the amount of gas to 2 moles, the volume of that system should go up. Because again, it's like the jelly bean example. If I go from 5 jelly beans to 10 jelly beans, we have significantly more volume, right? Double the volume, in fact, right, in terms of jelly beans. So there's an important thing for Avogadro's law and for a lot of these gas law, and it's actually what we call STP, which is standard temperature and pressure. And this will come up quite a bit as, especially if you ever take physics. This is a big thing in physics. This is also a big thing in like thermodynamics as well. We don't get into it too much, but it is important. It is important for us to sort of define a standard set of conditions so we can compare things together. Now, the standard set of conditions here are 1 atmosphere of pressure at 0 degrees centigrade or 273 Kelvin. That's standard pressure and temperature. Now, we can also express this in centigrade and millimeters of mercury, but remember, we're working in atmospheres and kelvins for most of our problems together. Now, can you convert easily between centigrade and Kelvin? Of course you can. And atmospheres and millimeters of mercury? Of course you can. But again, typically speaking, we're working in atmospheres and Kelvin here. Now, the other thing about this is if we have standard temperature and pressure, or STP, 1 mole of any gas, doesn't matter what the gas is on the planet, it could be carbon dioxide, could be methane, it could be helium, argon, whatever. That 1 mole of a gas will actually take an exact volume of 22.4 liters at standard temperature and pressure. But as we noted with Avogadro's law, right, that volume will change depending on the number of moles, and that volume can change based on temperature. So at standard temperature and pressure, all these conditions are true. 1 mole is 22.4 liters. Now, this 22.4 liters has also been called the standard molar volume. So conceptually, what we can actually look here is if we have 2 balloons, one has a mole of nitrogen gas or N2 gas, and one has a mole of helium gas. Well, if there's 1 mole and 1 mole, they take up, at standard temperature and pressure, of course, they both take up 22.4 liters. They both have 6.02 times 10 to the 23 particles, because remember, that's how many molecules are in a mole. But their molecular mass differs, right? We know 1 mole of nitrogen gas is 28 grams, and we know 1 mole of helium gas weighs 4 grams. Remember, we can derive that information from our friend, the periodic table. So let's do a quick little math problem in how to convert moles of a gas to volume at standard temperature and pressure, or STP. Now, the question asks how many moles are contained in 2 liters of nitrogen gas at standard temperature and pressure. So what do we need to know is the moles of nitrogen gas. What are we given? Well, we're given 2 liters. So what we can actually do is write a conversion factor, right? And that conversion factor is for every mole of a gas, it should occupy 22.4 liters, right? That's what Avogadro's law tells us. So what we can do is simply use the conversion factor that works best for us. And in this case, we want to get in moles. We start with liters, thus we have to use the one on the right, as we've been doing for the whole semester. So we multiply 2 liters times 1 mole over 22.4 liters, and we get a grand total of 0.089 moles of nitrogen gas, liters canceling in this case. So we can go from moles to liters and backwards simply by using this gas law equation. Now, this is where everything comes together and things become, I think, a little bit better and a little bit more easy to understand. But maybe you don't feel that way. We'll see. which we can express all of these gas laws and relate it to the number of molecules that we have as the ideal gas law. PV equals nRT, where P is volume, P is pressure, V is volume, N is the number of moles, R is what we call the universal gas constant, and T is our temperature in Kelvin. So what R is, it's this actually a set number. It's a constant of 0.0821 liters times atmosphere divided by moles times Kelvin. So this tells you exactly what its units are. And now we can also express it in millimeters of mercury, liters per millimeters of mercury, time over moles times Kelvin. But they're both essentially the same thing. So this is our ideal gas law. So what can we do with it? Well, let's look at a hypothetical example. We can ask the question, how many moles of a gas are contained in a typical human breath that takes in half a liter of air at 1 atmosphere of pressure at 37 degrees centigrade? So what we need to know here is the number of moles, right? That's what the question is asking us. We need to solve for N. So we have our equation PV equals nRT. We have pressure, we have volume, we have R because that's constant, and we have temperature. We're just simply solving for N. So all we need to do is just plug these bad boys into our ideal gas equation. Now, the first thing is we first need to convert centigrade to kelvins, right? That's what we have to do. Now, you'll remember back from one of our early classes together, Kelvin is equal to degrees centigrade plus 273. So we would take that 37 and add 273 to it, giving us 310 Kelvin. Now, we also know that the pressure is given in atmosphere, so we'll use this value for our friend R. And now we have everything in the right units, right? Remember, this ideal gas law only works if things are in the right units. So what we simply do first is actually solve for N by dividing both sides by RT, giving us the equation that we can derive from PV equals nR. Equation. So that's the ideal gas law, right? And the ideal gas law has different levels of uses, as do all the other gas laws. Now, what should you remember from this? Well, you definitely want to remember the ideal gas law, what it means. You also want to remember that equation that combines Boyle's, Charles, and Gay-Lussac's law together, right? Because those are the equations we're going to be using going forward. Now, this brings us to our final law, which is going to be Dalton's law, which we can look at the total pressure, or P total, of a gas mixture is simply defined as the partial pressures of all of its gaseous components. So when you look at a mixture of gases, say your average everyday breath you take, that average everyday breath you take of air is comprised of oxygen, nitrogen, argon, water, and carbon dioxide. And the total pressure, or P total, is simply the sum of all the pressures of all the individual gases in the mixture. So air contains all 5 of these gases, and the pressure is 101.3 kilopascals, or psi, as I've had written here too. But you'll notice that 101 is simply the sum of all of these gases. So that's what Dalton's law tells us, right? And so we could do a hypothetical example with Dalton's law, but I think it's a pretty straightforward one, right? There's no multiplication involved, which is nice. But what we can say is that a sample of exhaled air, so from your breath, contains 4 gases with the following partial pressures: 563 millimeters of mercury of nitrogen, 118 of oxygen, 30 of carbon dioxide, and 50 of water. They're all in the same units, so all we simply need to do, according to Boyle's law, is sum them, right? 533 plus 118, and so on and so forth, giving us a grand total, or a total pressure, of 761 millimeters of mercury. So those are our gas laws, how we describe how gases behave with a very simple set of terms: pressure, volume, temperature, as well as the number of moles. Now, what you'll notice about these gas laws is they'll start to apply to your average everyday life. So if you've ever blown up a balloon, what's happening when you blow up a balloon? Well, you're breathing air into the balloon. That's adding more molecules to the balloon. So if you think about that in the ideal gas law equation, we're changing n, or the number of moles. Thus, if n is changing, other things have to change with it, including pressure and volume and temperature. Right. So as you sort of go through your life, you'll notice that the ideal gas law and Charles' law and Boyle's law and Gay-Lussac's law all come up together quite frequently. You can apply it to a lot of different things. Like you could apply it to when you go flying in a plane, for instance, right? It'll teach you thinking about why your ears pop and things like that. So lots of cool applications of the ideal gas laws, in my opinion. Now, this leads us to describing some interesting aspects of two things we've talked about thus far, which is boiling point and melting point. Now, we have what's called an intermolecular force, which simply describes the attractive forces that exist between molecules. Now, we can define three distinct types of interaction forces between our molecules in a gas, liquid, or solid. Doesn't matter what state we're in. And this include London dispersion forces, dipole-dipole interactions, as well as hydrogen bonding. As we go from London down to hydrogen bonding, they increase in their overall strength. Now, the strength of these intermolecular forces determines a couple of things. The first is what state the matter is in. It determines if it's a solid, liquid, or gas at a given temperature. And if a compound, it also determines whether a compound has a high or low melting or boiling point, or boiling point. So let's talk about what those are, right? If they're important for changes in state between solid, liquid, and gas, and also orbit in shells around the nucleus. Thus, they are constantly in motion with one another. Now, because electrons are constantly moving in one another, their density, i.e., how much of them is in a defined volume, changes at a moment's notice. So, as electrons change in density, they create what are called temporary dipoles. So, just a slight change in the electrical charge of an atom, very much like a polar bond, right? But whereas a polar bond is a permanent change in electrons, a temporary dipole essentially changes in a fraction of a second. Like we're talking milliseconds of a change here. Now, this weak temporary dipole causes a weak electrostatic attraction between temporary dipoles between two molecules or two atoms. The more likely a dipole is to occur. Thus, the larger a molecule is, the stronger the intermolecular forces are due to London dispersal forces. So that's London dispersal forces. Again, kind of a weird thing, but clearly a very important thing. So let's just look at what this looks like conceptually, where we have a hypothetical molecule here. It looks a little bit like carbon bound to some hydrogen. So this looks like methane, though it technically could, well, actually it is methane. Sorry, I forgot. I didn't see my little thing there. So we have our friend methane here. Now remember, there's electrons, right, flowing around between these bonds, and they're moving force. That's what London dispersal forces are. Again, weird thing, but again, all due to the shifting of electrons in our molecules. So you can imagine if methane was much, much larger, the probability of a partial positive charge or a partial negative charge appearing should increase as the number of covalent bonds increase. And we can actually physically look at this again, where we have formaldehyde, where there's some dipole interactions here. Again, giving an interaction not just with one molecule here, but also with two molecules. So in this example, I gave you just two molecules working with one another. In this case, we have three molecules interacting with one another. Now, next up is hydrogen bonding. Um, um, and so, as I sort of mentioned, hydrogen bonding, at least in previous classes, I'd say, is a relatively common thing. But as you recall, hydrogen bonding arises due to polar bonds. Remember, we can determine whether a bond is polar by looking at the differences of electronegativity. Remember, we can go to the periodic table and find that. And anytime we see a covalent bond between two atoms, if the electronegativity differs by zero point 0.5, a polar bond is then formed. Now, which atoms do we most commonly see polar bonds occurring between? Well, in the purpose of this class, we commonly see polar bonds between carbon and hydrogen and oxygen, as well as nitrogen, as well as our halogens, so group 7a. Now, you'll remember is if we have two water molecules, there's two hydrogen bonds here. Now, what's going on here is there's an unequal sharing of electrons, which remember creates a partial positive charge on the oxygen and a partial negative charge. Sorry, partial negative charge on the oxygen and a partial positive charge on the hydrogen. These weak electrostatic attractions, very much like here, cause an attraction between the oxygen and the hydrogen, and that's what a hydrogen bond is. A attraction between a hydrogen and something else. That's what we're going for. And actually, hydrogen bonding is really, really common. It's a very, very important thing in biology, not just chemistry. And the example I'll give you here for what some hydrogen bonding looks like is actually in your DNA, right? And so your DNA, it's the double helix. It has DNA bases in the center, as I'm sure you guys have probably heard. Now, what holds your DNA, which is arguably the most important molecule in your entire body, is hydrogen bonding between the hydrogen of one DNA base and the oxygen of another, or a nitrogen of one DNA base and the hydrogen of another. Now, hydrogen bondings are stronger than all the other types. However, they're not particularly very strong, certainly not as strong as an ionic bond, and certainly not strong as a covalent bond. But certainly of what we've talked about for the intermolecular forces, they are the strongest. So this is what we have here. Just a nice little summary table of the three interactions we talked about. And remember, these interactions help shape what the intermolecular forces look like, giving molecules their different properties. And then we have some examples here of some examples of hydrogen bonding, dipole-dipole, and London dispersal. So as we mentioned before, what causes the changes in some of the physical properties of our molecules is these intermolecular forces, which is why we, of course, talked about them. Now, the boiling point, as you probably recall, is the temperature at which a liquid becomes a gas. The melting point is the temperature at which a solid is converted to a liquid. But the reality is, the stronger the intermolecular forces, so the more London dispersal forces, dipole, and hydrogen bonding you have, the higher the boiling point and higher the melting point. Now, conceptually, why is that? Right? Why does that make sense? Well, what does it mean to boil? Right? You're going from a solid to a gas. So you're changing not only the density of atoms or molecules, but remember, the molecules have to move faster to become a gas. So thus, to essentially to go from that state of liquid to gas, you have to break your London dispersal forces. You have to break your dipole-dipole interactions. You need to break your hydrogen bonds because remember, gases do not have any intermolecular forces. Solids and liquids do, but gases do not. So for things to increase in boiling temperature and melting point, they have to have more of these three intermolecular forces. So just to give you an example here, we have methane. Now, methane only has London dispersal forces. Its boiling point is minus 162 degrees centigrade, and it has a melting point of minus 183 degrees centigrade. Now, excuse me. That's methane with only London dispersal forces. Now, water has both London dispersal forces and hydrogen bonding. Now, you'll notice its boiling point is 100 degrees and its melting point is 0 degrees, significantly higher than methane. Now, we can look at another example of here of two hydrocarbons, propane and butane. Propane is what powers grills, right? And butane is like what's in lighters, for instance. Propane, you'll notice they have the same chemical formulas almost, right? C3H8 and C4H10. Now, they have the same molecules, which means they have the same exact intermolecular forces. However, because butane is larger, is likely to have more London dispersal forces. Thus, the interaction between two butane molecules is higher. Thus, butane has a higher melting point and a higher boiling point. So, two key things here is what determines boiling points and melting points is not only size, but also the amount of intermolecular forces and the type of intermolecular forces. So kind of a fun way to sort of tie together a lot of different avenues for the course that we've covered thus far, right? Relating things as the physical properties to actual physical atoms, which we then relate to interactions between those atoms. So again, really tying lots of threads we've talked about thus far in the course. So now the liquid state has some special considerations that we need to give it. So the first is evaporation, and I'm sure you guys have heard this term before, but evaporation simply describes the conversion of a liquid to a gas. And then we have condensation, which describes the conversion of a gas to the liquid phase. Now, when evaporation occurs, we're going from liquid to a gas. You would imagine to go from a liquid to a gas, you need more kinetic energy, right? Because gases have more kinetic energy. Thus, we would describe evaporation as a endothermic reaction, or endothermic change is probably the better word there. Why? Because liquids have less energy than gases. So to go from a liquid to a gas, we have to add energy. Thus, evaporation absorbs heat or energy from the surrounding environment, I should say. Now, condensation goes from gases back to a liquid. Thus, when something condenses, so you've seen this like on dew on your car in the morning or something like that, that is an exothermic reaction because it releases heat to the surroundings. Now, why is that? Remember, gases are moving faster, liquids are moving slower. So to go from fast to slow, you have to lose energy. Thus, the energy has to go somewhere, because remember, energy is not destroyed. Thus, that energy goes to the environment around them. Kind of a cool thing. Again, these a lot of these. One of the reasons I think this class is really fast, it's going, and eventually stops. Right, the pump shuts off. Now, if you ever thought yourself, why is that the case? Thing with vapor pressure is that vapor pressure does increase with temperature. So as you increase temperature, the vapor pressure increases with it as well. Now, the boiling point of a liquid, so to relate this back to a term we've discussed before, is equal to the temperature at which its vapor pressure is equal to 1 atmospheric pressure, or 760 millimeters of mercury. Kind of a cool thing. So let's look at this related to some intermolecular forces. So we have water. Remember, water has very, very strong intermolecular forces, and because it has hydrogen bonding and London dispersal forces. Then we have methane. It has very, very weak intermolecular forces. Remember, it only has London dispersal forces. Now, the stronger these intermolecular forces are, the lower the vapor pressure at a given temperature. Why? Because remember, vapor pressure describes the pressure at which these two gas molecules going between gas and liquid are at an equilibrium, right? They're equal. They're swapping back and forth at equal amounts. Thus, water, which has high intermolecular forces, has very few gas molecules, thus a lower vapor pressure. Conversely, our friend methane, very, very low intermolecular forces. There's very many more gas molecules and high vapor pressure. Now, to relate this back to where we started to think about the gas pump has relatively low intermolecular forces. It has higher intermolecular forces than methane, of course. However, the gas you put in your car has still lower intermolecular forces because it only has London dispersal forces. Thus, when the vapor pressure from a gas simply refers to not only how much pressure is in your gas tank, but also how much gas you have in your tank. Because remember, the more volume you have, it's related to pressure, right? They're proportional. So relating back to those gas laws that we saw. Now we have another term to describe the liquid state, which is viscosity. Now this is something you've seen in your average everyday life. If you've ever grabbed honey or molasses, for instance, and you try to pour those, what happens when you try to pour honey or molasses? They flow very, very slowly. That slow movement of those two liquids describes its viscosity. Honey is very, very thick. Molasses is very, very thick because they're very viscous. Conversely, water is not very thick because it flows freely. I'm sure you can do this experiment at your home if you want. Pour some water, pour some honey, which flows faster. The water, of course. Now, this is also related back to our intermolecular forces. Compounds that have strong intermolecular forces tend to be more viscous. Tend to be. Not always, but tend to be. Water, remember, has very strong intermolecular forces, but its viscosity is very low. It pours very freely. However, substances that are composed of very large molecules also tend to be more viscous. Why? Remember, large molecules have more London dispersal forces. Thus, they have higher intermolecular forces. Thus, their viscosity should also be higher. So, for instance, if we look at something like honey, honey is comprised of lots and lots of sugars, which are very large molecules. Hence, honey has a high viscosity, thus it feels thick. It has a high level of resistance to flowing. The same thing for molasses. Molasses is also comprised of very, very large sugars, lots of intermolecular forces, much more viscous overall. So typically speaking, these are the two things we see. Water does buck the trend here. Just as a note, water is, as we've discussed multiple times, is a very, very unique molecule. It really is. For a number of reasons, of course. So that's viscosity. Again, something you see in your average everyday life. The next is actually surface tension. Now, this is actually best described with water, but it does apply to pretty much every liquid on the planet. And now we can look at what's going on with water, and you might have seen this before, right? You have this insect, it's called a water strider, and you'll see it's just standing on top of the water. It's creating little indentations where its little feet, or I should say its little legs, they don't really have feet. Its little legs hit the water. But what's keeping this insect afloat is the surface tension, which simply describes the resistance of a liquid to spread out. Now, water actually has high surface tension because it has lots of intermolecular forces. Because what you think of surface tension is applying a pressure to your liquid. Now remember, pressure and volume are related. So as we apply a pressure to a volume, it should spread out. But water, because it has high intermolecular forces, actually is resistant to spreading out, at least to a point, right? And we can see that here, right? This insect is pressing down on the water. The water is pushing back with the surface tension, allowing the insect to stay on top of the water. So kind of a cool thing. Now, the other thing you could think about here is surface tension also comes into play with height. So jumping off bridges, for instance, which you definitely should not do because it's very dangerous. But jumping off bridges, such as say the Bunker Hill, I'm sorry, not the Bunker Hill, the Zakim Bridge in Boston, is very, very dangerous because of the surface tension of the water. So just relating that back to something really terrible. But I think the insect example is certainly not. So more intermolecular forces, higher surface tension. It's kind of a cool thing. Now, you guys have probably seen like leaves floating on water or even sometimes large things floating on water, right? What's causing these things to float on water are actually only being held up by the surface tension. It's kind of a cool thing. So that's going to be it for liquids. So we've talked about gases, we've talked about liquids. Now let's wrap this bad boy up and talk about some solids. Now, solids can be either classified as crystalline or amorphous. Something that's crystalline has a regular and repeating arrangement of molecules or particles that has a repeating structure. Whereas something that's amorphous essentially has a random assortment of things. So like you can sort of think about what a crystal looks like as if you had a nice box, right? And then you had a bunch of other nice boxes around it. They all form one nice box shape that looks like a crystal. And that's what crystalline means. Now, conversely, something that's amorphous would look like a blob of spaghetti, right? Just a giant pile of spaghetti with all the strands mixed in with one another. That's what amorphous means. So definitely, some things you've probably seen in your average everyday life. Now, what gives our properties to our crystalline solids includes four distinct things: ionic, molecular, network, and metallic. So those are our four distinct types of crystalline solids. So let's talk about it. So the first is what we call an ionic solid, and it's comprised of oppositely charged ions. So the example we've been using for pretty much the whole semester is our friend table salt or sodium chloride. You'll notice we have sodium gray, and we have chlorine in green. And you'll notice that one's charged positively and one's charged negatively, as we discussed. But they form this crystal, which is just a square, by arranging. But when you pick up table salt the next time, look at it. It forms little teeny tiny perfect square crystals. Why? Because it's an ionic solid. The next is our friend, what we call molecular solids. It's comprised of individual molecules that are arranged in a repeatable way. Now we can see our friend water here. This is a water as an ice, right? And you'll see water is arranged identically over and over again, right? You see this like standard shape here. It goes back and back and back, and then we see this shape goes back and back and back, and so on and so forth. That is a molecular solid. Now we have a network solid. Now we've seen silicon dioxide previously in this slide, but a network solid is essentially comprised of a vast number of atoms that are covalently bonded to one another. So in this case, we have silicon dioxide, where you notice that the silicon will bind to the oxygen, which will then bind to another silicon, which will bind to an oxygen and bind to another silicon, right? So that's why it's SiO2, because every silicon is bound to two oxygens, covalently, of course. Then we have the final one, which is a metallic solid, which is simply this repeating what we would call a lattice, but you can think of it almost like just like a bunch of blocks stacked neatly on top of one another. It's kind of the way it is in sort of conceptual 3D space. But basically, when something is a metallic solid, it's this group of metal cations, so positively charged things, surrounded by a cloud of electrons that are allowed to move freely in between them. So copper, for instance, there's a bunch of positively charged copper cations connected to one another, and there's electrons flowing freely with them. Now, if you know anything about wiring for electrical stuff, it's all copper wiring. Why? Well, copper wiring is a great conductor of electricity because of the type of solid that it is. It's a metallic solid. So those are our crystalline solids. Then we have our amorphous solids. Now remember, they have no regular arrangement of their particles. But the kind of interesting thing about our amorphous solids is because they can actually be formed very, very quickly um, when something cools from a liquid to a solid fast. So even if, for instance, silicon dioxide was in a liquid form and it was trying to cool to become a solid form, if that happens too fast, it can actually stop being a crystalline solid and become an amorphous solid. Now, that's one way we can create an amorphous solid, but actually the most common way we see the formation of amorphous solids is actually when something is very, very large. When things are very, very large, they typically will form amorphous solids because they simply become intertwined and folded with one another because of their size, right? Um, and note, and some examples of amorphous solids include things like glass, comprised of very large things, plastic, and rubber, again, both comprised of very large molecules. Excuse exactly 1 gram of that substance by exactly 1 degree centigrade. So you recall the equation we've been working with is mc delta T is equal to Q. Remember, Q is equal to heat, M is equal to mass, delta T is the change in temperature, and specific heat is C. Now, the idea here is, and what we sort of been sort of touching upon, but haven't really, talked about a ton, is that the larger the specific heat, the less something will change its temperature when it absorbs a set amount of energy. So we can look at some specific heats: aluminum, carbon, copper, so on and so forth, and then we look at water here at the end. Now, water, you'll notice, has the highest specific heat in this entire table at 1, right? 1 calorie per gram centigrade. Something else that has a high specific heat, such as our friend propanol, has a high specific heat. But what this tells us is that because water has a higher specific heat, it requires more energy to change its temperature than it does, to say, for propanol or aluminum or copper or so on and so forth. So it's an important thing. Now, the other thing you'll make notice of is that water's specific heat varies depending on its state. So in the lab, we've been working with liquid water, but gaseous water and solid water, so ice, have lower specific heats. Their temperature changes much more readily. So let's just do an example, just to refresh your memory of how this works. We can ask the question, how many calories are needed to heat a pot of 1,600 grams of water from 25 to 100? So we identify what we know, we identify what we don't know, we calculate delta T. Right, that's one thing we can do. In which case we have a change in temperature from 25 to 100. Times 10 to the 5 calories. So just as a refresher, remember, it's an important factor for thinking about state changes, right? How much energy something absorbs how much energy it takes to change something's temperature influences how much energy it takes to go from a solid to a liquid, and so on and so forth. Now, just as a sort of final sort of wrap up, just a couple of things. We have melting and freezing, as we talked about. Remember, melting is endothermic; it gives off heat. It consumes heat. And we have freezing, which is exothermic, thus it gives off heat. Now, the amount of energy needed to melt 1 gram of a substance is what we call the heat of fusion. So we can use this and remember, energy is conserved. So if it takes, say, 5 calories to melt something, it should take 5 calories to freeze it, right? That's the conservation of energy. So we can ask the question, how much energy and calories is absorbed when 50 grams of ice melts? The heat of fusion of water is 79.7 calories per gram. So we have the original quantity, and our desired quantity is calories. So we can write out a handy dandy conversion factor where the heat of fusion of water is our conversion factor, right? 1 gram over 79 calories, or 79 calories over 1 gram. Now we're trying to, as you'll recall, get calories. So thus grams needs to be in the denominator. Thus we choose the one on the right, right? 79, and we know that because of this expression here, right? 79 calories per gram, sorry. So we can solve this problem where we do 50 grams because that's how much we started with. The heat of fusion is 79.1 calories over 1 gram. Grams cancel out, giving us a grand total of 3,990 calories. And there are 3 significant figures here. We did start with 3 significant figures here as well. So just as I bring that back to the first class. Now, conversely, the amount of energy needed to vaporize 1 gram of water is called the heat of vaporization, going from a liquid to a gas. Now, remember, the energy required to go from a liquid to a gas is exactly proportional to go from a gas back to the liquid, right? Energy is always conserved. So we could do the same calculation here, but I don't really think we need to do that. It's the exact same one. And then the final thing we'll make mention, oops, sorry about that, is with this idea of state change is sublimation and deposition. So sublimation goes from a solid to a gas, and deposition goes from a gas directly to a solid. That's pretty much it. And again, the energy required to sublimate should be exactly proportional to the energy to deposit, I should say. So easy questions to answer are exactly like this, right? This one that we went over. So wouldn't worry too much about it, but just know what it means. And if I gave you this problem, you should be able to solve. And this is just a handy table that describes what melting is, freezing, vaporization, and so on and so forth. It also tells you whether it's exothermic or endothermic. You definitely want to remember exo and endothermic. They come up not just in chemistry, they're going to come up in anatomy and biology and cell biology and so on and so forth. So definitely remember these guys. They're going to come up quite a bit. Now, this gives us to something we're actually going to do in lab, which are heating and cooling curves. Now, a heating curve actually displays how a substance temperature changes as heat is added. So we start at A, which is at some temperature. And as we go up the y-axis, temperature increases. As we go right on the x-axis, we add more and more heat. So we start at some state and we increase the temperature, right? Because we're adding heat. Then we start adding more and more heat again, getting us to state D, which is the boiling point. And you notice we keep adding heat at the boiling point till we reach state E, which gives us our gaseous phase. So what you'll notice here is that it's not like an instantaneous thing. Something doesn't automatically just boil or automatically just melt, right? It requires constant input of energy for that change to occur. So think about this when you put a pot of water on the stove, right? So pretend you put a pot of water, put a pot on the stove, and you put a big block of ice in there. You turn the heat on full blast on the stove, and what happens? The ice will gradually start to melt. It doesn't all melt instantaneously, right? Because you have to keep adding heat and heat and heat. But eventually, you'll add enough heat that the entire block of ice will melt into liquid water. Then you keep heating it up and heating it up and heating it up because you're adding more and more energy to it. And eventually, you'll notice it starts to bubble a little bit, right? Starts to boil. And that will boil and boil and boil and boil. And if you leave it long enough, and I don't recommend you do this because it's very bad for your pots and pans, just as an FYI. Uh, but after enough heat added, all that water will boil out and will all become a gas again. So we think of boiling and melting as sort of being like just discrete states, and they certainly are. But there is, like, again, an energy required over time to do it. Again, it's not just like I hit 100 degrees, bam, it's melted. No, it's like I have to hit 100 degrees and or 0 degrees, and I have to keep adding stuff. Now, conversely, we have this heating curve. We can actually look at a cooling curve, which is the exact opposite, where we exist as a gas. The temperature drops from V to W, and that's the condensation temperature. But again, we have to keep removing heat, right? This is the exact opposite of the curve we saw before, because as we go from left to right on the x-axis, we're removing heat. And so as you go from WX, we're removing heat, that's condensation. And eventually everything condenses to form a liquid. And then we have to keep removing heat. And then we hit the freezing point. But again, we have to keep pulling heat away until it hits Z, where eventually it's all a solid. And then we can keep pulling it away to change the temperature. But again, there are these little stop gaps when we look at freezing and melting and so on and so forth, which again can easily be visualized in these heating and cooling curves, which you will have taken a peek at during lab. But that's going to be it for today's lecture. I hope you guys learned a little something. If you have any questions, feel free to reach out. But otherwise, you guys are doing well, and take care.